So continuing on, this is just stating the Pythagorean theorem that we've already covered. The hypotenuse squared is equal to the square of one leg plus the square of the other leg, only for right triangles. And then a reminder that if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and leg of a second right triangle, then the triangles are congruent. We've actually covered that already. There's a lot of repetition in this material, but repetition is good. Reminds us there are so many geometry rules that it's always good to have a reminder. All right, so when we're talking about Pythagorean theorem, you can use c squared equals a squared plus b squared, but also sometimes there are some what are called Pythagorean triplets that you'll see all the time, like the 3, 4, 5. If you have a right triangle and one side is 3 and the other side is 4, the hypotenuse is going to be 5. And we see this one all the time. So rather than having to do c squared equals a squared plus b squared, if I saw this triangle, I could just say, oh, that side is 4, because that's a 3, 4, 5 Pythagorean triangle. And then I could also have triangles that are using Pythagorean triplets that I multiply these numbers by a natural number, a counting number. So even if you have like a little child, little son or daughter, or a little niece or nephew, and you ask them to start counting, they'll say 1, 2, 3, and they'll go up as high as they can go. But they start at 1. You know what? That's only natural. When you're asked to count, it's only natural to start at 1. So the set that starts at 1, 1, 2, 3, 4, 5, and the counting numbers, those are called the natural numbers. So we have a standard Pythagorean triplet, 3, 4, 5. If I had a triangle and this was 30 and this was 40, if I multiply 3, 4, and 5 by 2 or 3 or 4 or 5, or in this case 10, I would know that that's 50. This is basically your 3, 4, 5 triangle, only multiplied by 10, multiplied by a counting number. So any multiples of 3, 4, 5 are also right triangles. So coming down here, you see the 3, 4, 5 triangle a lot. Sometimes you'll see the 5, 12, 13. So some math students have actually memorized some of these Pythagorean triplets. Of course, you can always use c squared equals a squared plus b squared and do the calculations. But you can save yourself a little time if you memorize these combinations. Most people memorize the 3, 4, 5. But the 5, 12, 13, of course, the 13 would have to be, look at I drew it wrong. The 13 would have to be the hypotenuse. And 8, 15, 17. So those are some Pythagorean triplets, or multiply the triplet by a counting number. All right, here, so this kind of used the shortcut I just used. If I have a 3, 4, 5 right triangle, and I have a 6, 8, 6, 8, 10 triangle. I've multiplied that by 2, multiplied that by 2, and that by 2. These two triangles are similar. Why? Because 5 is to 10. That's the same proportion as 3 is to 6. That's the same proportion as 4 is to 8, which they can all be reduced to 1 to 2. The three sides are in proportion. If the sides are in proportion, that would be side, 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 similar. We've also had side, angle, side, similar. And we've also had angle, angle, similar. So this point down here is just saying, you know, a 9, 12, 15 or a 12, 16, 20. These are all similar triangles to the 3, 4, 5 because we're just multiplying the 3, the 4, and the 5 by a constant, basically. Now, we can also figure out, we know that if c squared equals a squared plus b squared, we know it's a 90 degrees or a right angle. But you know what? If c squared is greater than the leg squared, that's an obtuse. C is obtuse. If c squared is less than the sine squared, then c is acute. So let's see if we can tell what kind of triangles these are just by its side lengths. Well, the first thing is we have to make sure that these are valid side lengths. If you remember the triangle inequalities, any side has to be greater than the difference of the other two sides and less than the sum of the other two sides. So 7 has to be greater than 5 minus 4, but 7 has to be less than 5 plus 4. Are these even valid side lengths for a valid triangle? So 7 is greater than 1 and 7 is less than 9. So let's see. C squared equals a squared plus b squared. Of course, c squared, there's going to be, c is going to be the longest side on a right triangle. So 7 squared is 4 squared plus 5 squared. Oh, sorry, we don't want to put the symbol in there. We want to see if it's equal, less than, or greater than. We want to fill that symbol in at the end. So 49, 16 plus 25, 49, and 41. These are valid side lengths, but 49 is greater than 41. So this is an obtuse angle because c squared is greater than a squared plus b squared. All right, let's look at the second. First of all, let's make sure it's valid. Is 8 greater than 7 minus 6? And is it less than 7 plus 6? 8 is greater than 1 and is actually less than 13. So it is a valid side lengths. Let's do c squared, a squared plus b squared. 8 squared, 6 squared plus 7 squared. So 64, and here we have 36 plus 49. 64 and 36 plus 49 is 85. You know what? 64 is less than 85. So this is an acute triangle. All right, 9, 12, 15. That sure looks like a 3, 4, 5 triplet. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. We know that these side lengths are valid and that it is a right triangle. We don't even have to do the work. We know that it's a Pythagorean triplet. And how about D? Is 9 greater than 4 minus 3? And is 9 less than 4 plus 3? You know what? 9 is not less than 7. This is not even a valid triangle. This is not a triangle. This would not be a closed figure. So not even a triangle.